taking your notes. Okay, we're discussing section 6.4, part 1, the fundamental theorem of calculus. As the name implies, it's a very, very important theorem. It pretty much connects the fall and spring semesters, as I talked about in big ideas for week 3. So it was independently discovered by Sir Isaac Newton, as well as Leibniz. I don't know his first name, but he's also considered one of the founders of calculus. You might have heard they sometimes talk about like Leibniz notation. Anyway, these are two dudes 200 years ago who independently discovered the fundamental theorem of calculus. And it does serve as a foundation for also much of the physical sciences. So a lot of those people who major in physics or engineering or stuff like that, calculus is a big deal in those courses. And in order to understand calculus, you got to understand this theorem, because this theorem is kind of the heart of calculus. So before we look at FTC, and I call it FTC for short, because it's hard to keep saying fundamental theorem of calculus, keep writing it out. So FTC is the abbreviation for fundamental theorem of calculus. Before we again look at it, let's examine the integral as a function, specifically this function here. So remember, capital F is the antiderivative of little f. Just capital F is antiderivative of little f. And interestingly, our lower limit we'll still call A, but our upper limit I'm not going to call B. I'm going to call X instead. You'll see why in just a little bit. The upper limit we're going to call X. Okay, we're going to do a little exploration. So let's have a general function, as you see off to the right. We know the area of the curve from A to B is that, right? So if I were to shade all this, right, that'll equal the area. We know this, right? But let's pick an X value in the interval from A to B. So let me erase what I just shaded. And let's pick a random X value in A to B. Let's say X is over here. And let me shade that. Let me do yellow. We'll shade that as yellow. Okay. So shading as yellow. And we write the integral that's represented by it. Well, the integral that's represented by the yellow area, so the yellow area is simply from A to X, not A to B, from A to X of f of t dt. And by the way, I'm using t instead of x here, because it can get very confusing when the upper limit has the same letter as the expression itself. So, and again, remember, these are dummy variables inside of the function, or dt, dx, du, whatever. So it doesn't really matter. And that should, by the way, that should be a t, not x. My apologies. Let me erase that. Those should be t's. Okay, so the key idea is that we have different choices for x resulting in different areas, right? So what if I put x over here? Then the area would get bigger, right? Or what if I put it closer to B? Or what if I made it closer to A? The bottom line is that an integral represents an area, right? So thus this area is a function of x. So area of the curve is a function of x. This is what this represents. Area as a function of x is represented as a definite integral. We kind of talked about that anyway, but this is just really just driving the point home. I'm abbreviating definite integral as def period nth period. So we write a of x simply as the integral from a to x of f of t dt. You could also write it other ways too, if you like. You could write it, as f of u du, or you could write it as f of theta d theta. It's totally up to you how you want it, what variables you want to use. So you use any variable you so desire. You can use any letter for the input of the function. Totally up to you. But the bottom line is that if you're starting at A and you're going towards some x value in your interval, then that area can be expressed as a definite integral. That's what's happening here. And sometimes we call this an accumulation function because you're accumulating area, right? It's or you could, obviously, if you move x closer to A, then of course you have a lower, lesser area, right? That's one type of explanation we just did. Let's look at another. This one's going to be very important. So we're really going to drive this point home I think very well. So again, this will help you to understand integral functions. Functions defined by integrals involve finding areas, as we know now. So we're going to start at -2, and we're going to go towards x. But x is going to, vary. So first off, you graph, this is y equals 4. Okay. It's y equals 4. And we're starting at -2, of course. Let me do this in blue. And we're going to be sweeping some area. In fact, we're going to replace x here. So this x is being used to replace that. So these are going to be the upper limits, all these different x values. That's going to be the upper limit of our integral. And please ask questions, by the way, because this is such an important thing that I'm doing with you guys. So upper limit of the integral. Let's actually start with -2. So let's say I want to evaluate a of -2. So I'm going to evaluate that right now. So you're integrating simply from -2 to -2 of your function. Well, guess what? The lower upper limits are the same, so that's just 0. Let's say I want to integrate from -2 to -1 now. Well, if I do that area, just use geometry. What's that area? That's just going to be 1 times 4, so that's going to be 4. Let's keep going. Let's sweep from -2 to 0. What's that area? 8. Let's sweep from -2 to 1. What's that area? 3 times 4 is 12. Let's sweep from -2 to 2. What's that area? 16. 4 times 4. Let's go the other direction. What if I sweep from -2 to -3? So remember we talked about this? So if I were to do a of -3, so now I'm going from -2 to -3 of 4 dt. Remember, it's going to be the reverse if I reverse those using our properties. And you typically want the lower limit to be less than the upper limit. So in that case, it's a negative area when you're going from right to left. We call that a negative area when you go from right to left instead of left to right. So this would be -4, and that'd be -8. So based upon what you see in this table now, can you come up with an equation for y? It's going to be a linear equation. If you know what that linear equation is, please type it in the chat. What linear equation do you think we can use to represent a of x? I know a of x is an integral, but the table kind of indicates it's a linear function. So anyone can feel free to type in if they think they've got it. I'll wait for a couple more people to chime in. Okay. See, I see 3 people chimed in. Some people are saying 4x plus 8. Good. It's 4x plus 8. Because if you think about it, your y-intercept is 0, 8. So y equals, mx plus b, right? So your b is 8, and your slope is 4. So y equals 4x plus 8. Or if you think about it, you could also write like this too. If you want to do point slope form. Because we do have -2, 0 as a point there. I mean, same, or you could factor out the 4 if you want. It doesn't really matter. So good, cool, okay. So generally speaking, it's essentially we're doing 4 times x plus 2, or 4x plus 8. Now, why is that important? This is the essential part. This is the aha, the light bulb type moment coming up. So we can come up with this another way. Again, remember, we're starting our integral at -2. We're going towards x. I have some area that I'm trying to find. Well, how would I find that area? Isn't that just a rectangle? Base times height? So the base is x minus -2. The height is 4 because it hits y equals 4. Well, x minus -2 is x plus 2, so you get 4x plus 8. Let's look at this one more time. And actually, that's going to be the true aha moment. Sorry, I was a little premature there. But it makes sense, right? That, we got that as an answer for the area function because, the difference between these two is x plus 2, and the height's 4. And that's, we see that from the table. Okay, this is really going to drive the point home. And it's going to be a big deal that leads us to the third page here. Okay. So here I have an accumulation, sorry, another area function, right? So what I'm graphing now is y equals t minus 1. So you have a y-intercept of -1, slope of 1. Oops, sorry, slope of 1. Okay. And we're starting the integral at 1. So you're starting it here. Now, if I go from 1 to 2, let's go from 1 to 1. If I go from 1 to 1, that's just 0. Right, we know this. Start with an easy one. If I go from 1 to 2, remember it's a triangle, a right triangle. What's the area of a triangle? You guys should know 1/2 times base times height. times base times height. Your base, of course, is 1. Your height is also 1. But you got to take 1/2, so it's actually 0.5. What if I integrate from, see, that's why I call it area accumulation. I'm accumulating area, right? 1/2 times 2 times 2. Sorry, let me write that more neatly. It's 2. What if I integrate from 1 to 4? So it's 1/2 times 3 times 3, 4.5. What if I go backwards? If I go backwards, it's going to be negative 0.5. It's still 0.5, obviously, is the true area, but it's down below the x-axis. Or, oh, I lied. It's not negative 0.5. Sorry. Yes, I'm below the x-axis, but I'm also going right to left. So yes, you do have an area. So when you integrate from, if I do the integral from of a to 0, I'm integrating from 1 to 0 of my function, right? So it is a negative, it is below the x-axis, but it's also going from right to left. You're doing two negative things, so they actually cancel out, so it's actually 0.5. Sorry about that. I'm glad I caught myself quickly. So yes, it's below the x-axis, but they're also going right to left as well. And then this one will be 2. Yes, the area that, 1/2 times base times height, you go from right to left, but below the x-axis, so double negative. Now, does anyone want to take a stab as to what a of x would equal here? Anyone have a general idea of what a of x could equal here? It's not terribly easy. Don't worry. Actually, you know what? Don't worry. Well, let's work out together, because it is kind of hard to figure out, because it's not linear. I can say with total confidence, it's totally not linear. So again, let's look at the graph of y equals t minus 1. That's this over here. Let's look at it just a little differently. That's at 1, right? We'll call this generally at x. And oh, there's a question in the chat. Not quite absolute value, but you're on the right track. Someone says something about absolute value. You're on the right track, though. I'll shade anything above as yellow. And anything down below I'll shade as red. Let's say we go to like, I don't know, let's say we go like -3, for example. I'll shade as red. So here's what we're noticing. And then again, question in the chat. Nico, close. Nico said x squared plus x. You're getting warmer. It is quadratic. I will say that. So here's what's happening. Generally speaking, the area of this triangle, again, is 1/2 times base times height, right? Well, wouldn't your base be right here? Which would be x minus 1, right? Wouldn't your height also be x minus 1? Because if you plug an x into the function, because it's touching it right here, if I plug an x into y equals t minus 1, it's also x minus 1. So my area would actually be 1/2 times x squared minus 2x plus 1. If I distribute, I get 1/2 x squared negative x plus 1/2. So that's going to be my area function. It's going to be a quadratic function. Someone put absolute value, but it's not absolute value. I know it looks like it. But again, we're just graphing a of x. We're graphing t minus 1. but we're trying to gather what a of x would equal from the graph of t minus 1. So this is not obviously a of x here, this graph here. This is still t minus 1. But like, for example, what if I integrated this from 1 to -3? Well, if I look at this is 4. This is the length of 4 as well, because if I plug in -3, this goes down to -4. So if I were to calculate this area, 1/2 times 4 times 4, I get 8, right? Technically speaking, you would actually make both these negative, but they would cancel out anyway. So yeah, it's kind of interesting a little bit what we're seeing here. So this brings me to something called, or brings me to the next page, which we'll get to the FTC in just a sec. So again, we got 1/2 x squared minus x plus 1/2, right? And give me 1 second here. Okay. So again, if I integrate from 1 to x of t minus 1, I got that, 1/2 x squared plus 1x plus 1/2. The right-hand side is an antiderivative of x minus 1. Because what if I took the derivative of this? If I took the derivative of this, I would have 2 times 1/2 x minus 1 plus 0. I would get x minus 1. So it's interesting. We're starting to see this connection between the antiderivative and the area. So, and again, if I took the derivative of my integral, remember my integral equal that, I did get x minus 1. So essentially, by doing the derivative of an integral, this right here is super important. By doing the derivative of of a definite integral, it gets me back to the original function. So it's almost like d dx and this integral here are inverses of each other. It's almost like they undo each other. And that right there is the fundamental theorem of calculus, part 1. What it states, and I'll get to this part in just a little bit off to the right here. What it states is that if little f is your original function, if it's continuous, and so capital F is the antiderivative, then by taking the derivative of the antiderivative, so this is what this is. This is the derivative of the antiderivative, because capital F is considered the antiderivative of little f. So if you do the derivative of the antiderivative, you just get back to the original function. So essentially what you're doing is you're doing d dx of the integral from a to x. So you do a, because f is, remember, the integral of the antiderivative, which is from a to x of f of t dt. So now we're starting to see the connection between the geometry and the antiderivative. So you use both. So it's not just the area you're accumulating, it's also going to be the antiderivative. So that's essentially what is going on here with the fundamental theorem of calculus. By the way, let's now look at the box in the top right corner. What if I decided to change the lower limit to -3 instead of instead of +1. Well, let's look back at this here one more time. And actually, this is what I was supposed to do. Let's say you're at -3, right? And you're integrating from -3 to 1. If you were to work, or say call this, generally speaking, let's say your integral is this, from -3 to x of f of t dt. And x is right here. So yes, this area was 8. Remember, it's a double negative because you're going from right to left, and it's below the x-axis. So we just say it's 8. So that integral would equal, actually I take it back. If you're starting at -3 and going towards 1, that's actually gonna be -8. Because you're not going from right to left. You're going from left to right, and it's below the x-axis. So that's -8, then plus the integral from 1 to x of f of t dt, which we knew now was 1/2 x squared minus x minus 1/2. Sorry, plus 1/2. So then this would become 1/2 x squared minus x minus 7.5. So that's what this would be. If you started the integral at -3 instead of at 1, from -3 to 1, I know that area is -8 because below the x-axis. Again, going from left to right, below the x-axis, negative area. And then integrate from 1 to x, which we solved earlier, which was 1/2 x squared plus minus x plus 1/2. If I combine, I get this. Well, if I do the derivative, so now if I go to the box down here, if I do the derivative of this integral, which was 1/2 x squared minus x minus 7.5, if I do that, I still get x minus 1, because 7.5 actually goes away because it's constant. So what we're starting to see also is that the lower limit doesn't matter. That's also another part of FTC we need to keep in mind, and we're going to do some examples of that in just a little bit. The lower limit won't matter when you have this. Let's talk about some implications. Let's do some examples. Once I get to the examples, it'll start sinking a little better. There's some implications we have to state first. Remember, every continuous function will have a derivative. Will be the derivative of some other function. That's what this is telling us here, is that if little f is the derivative of an antiderivative, and we're assuming continuity, every continuous function is derivative of some other function. Also, every continuous function has an antiderivative. The antiderivative will also be continuous on a to b, because fundamental theorem states that df or dx exists everywhere, so therefore it's differentiable, therefore it has to be continuous. If you're differentiable, you are continuous. We talked about that back in the fall semester. So anything of this form will be continuous, provided that your original function is also continuous. And the process of integration and differentiation are inverse operations, so they undo each other. That's what FTC part 1 is all about. And remember this notation, the ddx, that is actually a derivative operator. So remember, like when we saw like ddx of something, you just took the derivative. In this case, that was like secant squared, right? But remember that this is a totally different thing though. This is actually y prime times tangent x. And y prime, of course, if your y is tan x, then that would be secant squared x times tan x. So the reason why this is put in this is some people get confused in notation. D dx means I want the derivative of tan x. Dy dx means the derivative of tan x times tan x. So be mindful about your notation. Don't blur this, please. Again, I talk about the attention to detail, precision. I'm not lying. It's a big deal. You gotta be super precise with this stuff. All right, I may have blown your mind a little bit. I know it's a lot of stuff. That's why I'm doing over 2 days. Let me do the examples. Let's take a break. Let's come back and do the worksheet. Things will start coming into place. Just gotta trust me here. Again, I'm recording, which is good, so you can always rewatch this if you need to. So here's our first example. You're asked to find d dx of this integral using the fundamental theorem calculus. We talked about the d dx of an integral, they just undo each other. So it simply just becomes sine x. That's all. And you don't put plus c because we're not doing an see, this right here will be an antiderivative, but then you're doing a derivative afterwards anyway. So like, for example, what if I integrated, just so you guys can see this actually a little bit more clearly. This is just a quick aside from the examples. What if I integrated from 0 to x of, I don't know, say 2t plus 1 dt. We know the antiderivative of 2t. The antiderivative is t squared. And the antiderivative of 1 is t. And of course, it's a plus c. We know this, right? And remember, we talked about how you plug in the upper limit. So you plug in x, so it comes x squared plus x plus c. And you plug in 0, which is, again, 0 squared plus 0 plus c. The c's cancel, so you get x squared plus x. Then do the derivative of that. That's going to be 2x plus 1, which is precisely what was inside here in the first place. And would it matter if I put like a 1 here? Absolutely not. It wouldn't have mattered. Fine, you'd have this. You'd have x squared plus x minus 2. But when you take the derivative of that, it goes away. So you'll still get back to 2x plus 1. So what we're seeing here is that even if you change this, it doesn't matter. The lower limit doesn't matter for FTC part 1, which we're talking about right now. So is this going to be sine x again, even if you had a negative pi over 4? It doesn't matter, because if you actually did the integral, we know the answer to 2t plus 1 is t squared plus t, plus c, of course. Plug in your upper limit, just x, so it's in terms of x. Plug in lower limit, whatever number you want to choose. Work it out, then do the derivative. You get back to the original thing, and whatever constant you have would just go away. So it doesn't matter. So it's totally we just neglect it. We don't worry about it. And again, I'm going to talk more about this with you guys tomorrow as well to really drive this home. So here, for example, don't actually do the because actually I don't even know what the antiderivative of this is. That's going to be, actually, you could use some really weird techniques, which is beyond the scope of this course. But you're asked about dy dx. So basically you're doing d dx of the integral from -2 to x of 5 over 3 plus t squared dt. Guess what it equals? 5 over 3 plus x squared. Done. That's all you're doing. That's it. That's the answer. Simply replace t with x. That's all. Now here, the lower limit is actually, or the constant, is now upper limit. So you have to reverse it. You do have to reverse it. You want the lower limit here, and like that. Then we do dy dx. So doing d dx. So again, you have to reverse the limits of integration. D dx of this entire integral here. We'll get to the question in just a sec. Secant theta d theta. So it's going to be negative secant x. That's all. Question in the chat. Yes, I did say dy dx is not the same thing as d dx. Yes, I did say that. I don't think no, dy dx was a derivative of this. I'm not doing dy dx of the function. I'm doing dy dx equaling d dx of the function. So just make sure you're clear on that. That's what I was doing as an operator. And then that becomes dy dx, which is what I want to find, which is d dx of the integral, because the integral equal y. So I just want to make sure we're clear on that notation. Okay, never mind. Okay, you got it. Thank you for clarifying. No, you don't write secant theta because what's happening is now you're replacing theta with x. Remember, I just did that little demonstration. Let me, okay, it's gonna take forever to undo it. Remember that I did a little demonstration with t squared plus, sorry, 2t plus 1, and I took the antiderivative, which is t squared plus t. Then I plugged x in, so you got to replace whatever letter you see here with x. So the answer is going to be in terms of x. Let's do example 4. Let's take a little break, and then we'll come back and do example 5. So this one's going to be a little funky. You don't have plain old x up here, just so you know. You have 5x cubed. So the problem here, upper limit is not plain old x. Again, let me just as a quick aside, and then we'll come back to this actual problem. Remember, I did this with you guys again. We went from 0 to x of 2t plus 1, right? We just did that a few minutes ago. 2t plus 1, right? dt. What was antiderivative 2t plus 1? T squared plus t plus c, right? Integrate from 0 to x. We did all that stuff. What if I did x squared here as the upper limit? What if I did that? What happens? Well, of course, I got to plug in x squared for t. So it comes x squared squared plus x squared plus c. And of course, minus, I plug in 0, 0 squared plus 0 plus c. The c's cancel. So I'm getting x to the 4 power plus x squared. Now, if I do the derivative of this, that's part of the FTC, right? Remember, you're doing a derivative, antiderivative. So it's now connecting differential integral calculus, right? That's why it's called fundamental theorem calculus, connecting all the old stuff with the new stuff. So if I do d dx of that expression, I get 4x cubed plus 2x. Well, if I think about it, I could replace t with x squared and get 2x squared plus 1. But you got to do a chain rule, that x squared. Then comes 2x. If I distribute, I get 4x cubed plus 2x, which is exactly what I got down here when I went through this by brute force, by doing the antiderivative, plugging in x and 0, then taking the derivative. You could just realize that you're essentially replacing the t here with the upper limit, but then you got to do a chain rule. We didn't do it earlier on because the derivative of x was 1 anyway, so we didn't worry about it. The chain rule is always around us the whole time. So to do this one, all you would do is you would say, okay, if I do, the derivative of all that junk, tan t squared minus 3t dt, oh goodness. Let me write more neatly. Well, yeah, replace the t with the 5x cubed, of course, is what we got to do. So it's tan of 25x6 minus 15x cubed. But then you got to multiply it by 15x squared, because that's part of the chain rule. And so that's another thing you have to keep in mind. So when you do ddx of lower limit and then g of x, we have some function in the upper limit in terms of x. You still do f of g of x, still replace your variable with the upper limit, but also multiply by the derivative of that upper limit. And that would be a great place to take a break. So we'll come back. We'll do another one that's a little more complicated, like example 5. The more I think about it, I don't want to do example 6. I think that's opening a can of worms. That might be better. And so I'll reduce the homework, because a couple of homework problems that deal with example 6, and I just don't feel comfortable doing that. But you guys need to practice. So we'll take a 10-minute break. We'll come back around 10:30ish. We'll do example 5, and we'll do some of the worksheet. I'll try to talk to you guys individually about your tests. Come back about 5 minutes before class is over, but let's come back in 10 minutes. There is a question in chat really quickly. Yeah, you can leave your answer like that. Yes, someone's saying, yeah, totally leave your answer like that. Actually, I don't know how else you would want to write it. So yeah, leave it like that. Can you please read what I just wrote? Yeah, it's a tangent of 25x to 6 minus 15x cubed, all that times 15x squared. So actually 15x squared, if you want, we could probably put it to the left. That might have been actually more proper to do that instead. 15x squared times all that jazz. Okay. Oh, the word's in red, sorry. Oh, still replace the variable with the upper limit. So that's what is being shown right here. Still replace the variable with the upper limit being g of x, but also multiply by the derivative of the upper limit. Let me pose a text box really quickly. So still replace the variable with the upper limit, but also multiply by the derivative of the upper limit. And let me put that as a text box so you guys can see it. Okay, so you can see it right there. Okay, we'll take a break. I'll keep this up, Sharon, but let me pause the recording. Let's resume. Okay, so recording again, we got example 5 of the section 6.4 notes. This one is a little bit interesting. The lower limit is not a constant here. So we have to get a little tricky here, or sneaky. The lower limit is not a constant here. Now, again, we have to be a little resourceful and creative. Let's say you pick a random constant called a. This is a true statement. What I'm about to write right now is totally a true statement. You could say that this integral from 5x x squared of sine 3t dt could be written like this. 5x a sine 3t dt plus the integral from a x squared sine 3t dt. You totally can get away with that, and here's the reason why. Remember we talked about additivity, that property. Like let's say this is 1, say this is 10, and say this is 4. I'm just making those numbers up. So I got some sort of funky curve that does this, right? Well, clearly the integral from 1 to 4 plus the integral, I'm just writing little squiggly lines here, from 4 to 10 of some function is going to equal the integral from 1 to 10 of the same function, right? That's because these link up. So why not do the same thing here with 5x and x squared? I don't know what x is exactly, but there's no harm in doing that. You totally can get away with that. And don't worry, oh, well, how do I know x squared is going to be bigger than 5x? Don't worry about that. You just rewrite the integral in this way. So this is using the additivity property. So you're getting a little creative here. By the way, the College Board loves this kind of question. And they sometimes will sneak this into the free response if they go back to the traditional way with multiple choice and free response. They love this question. So then what you can do is you can reverse the order of integration. So A is on the bottom now. And then do your FTC. So now you do the derivative of this bad boy, right? Because that's what we want. So if I take the derivative of this guy here, doing d dx here now, because that will get me dy dx. And if I do it correctly, I take the derivative of the first one, so you replace t with 5x, so it's negative sine 5x, but then chain rule times 5, plus replace t with x squared, so sine 3x squared times 2x. And there you go. Oh, yikes, I'm sorry. I was supposed to multiply 5x by 3, it should be 15x. My apologies. Glad I caught myself there. It should be 15x. Because you're replacing t here with 5x, so it's 3 times 5x, and you're replacing t here with x squared, so it's 3x squared. Just clean up just a tad. Negative 5 sine 15x plus 2x times sine of 3x squared. Okay. Voila, there you go. Now you're going to practice these skills. We'll do them in individual breakout sessions because just for privacy reasons, I just want to make sure, if I'm talking about a test, I'm not talking with other people listening. So I'll put you guys in your individual breakout rooms. We'll see how many people I can talk to during those 15 minutes because we do have to come back and debrief quickly at the end. But you are going to work on worksheet 7A. So worksheet 7A looks like this. Fundamental theorem of calculus, right? That's what we worked on. You're asked to find the derivative of capital F, which is what we've been doing all along. So there's a total of 8 problems here. You can see that you have a lower limit of negative 4 and x up top, lower limit of negative 3, x up top, lower limit of negative 1, x squared up top, 4, 3x, 2, x cubed. Then you have like these with like example 5. Number 6, 7, 8 is like example 5. And the answers are below, so you can check to see if you're doing these right. They should be pretty straightforward. If you got this, you should be able to get all this done in 15 minutes. If you got this. If you're stuck, call me over, but I'm gonna start hopping into different breakout rooms. Probably just going, just giving you guys some feedback about your test. Tomorrow we're doing more of this stuff, and so we should have more time for breakout sessions. And I should be able to get to give everyone feedback that you guys deserve about how you're doing this class, because we're on the midterm session. What's kind of crazy to think, right? We're almost done. So it's crazy, just nuts, but it is what it is. Okay, so let me stop the recording.